Okay, so let's go over this example. Okay, so we're choosing a card at random from 52 playing cards. Okay, what's the probability of getting the 8 of diamonds? Well, how many 8 of diamonds are there in the deck? There's only one. So because there's only one, the probability of drawing it, that is choosing it from the deck, is 1 out of 52. What about the probability of choosing an ace, of drawing an ace, that is? Well, there are 4 aces in the deck, right? One for each suit. So the probability here would be 4 out of 52. Now the probability of not drawing a heart. In other words, you want to draw a card that is not from the suit of hearts. Well, you could probably count it directly, but let's do it this way, as I have here. There are 13 hearts in the deck, so the probability of drawing a heart is 13 out of 52. But we want the complement of that. That is, we want the probability of not drawing a heart. So in this case, we would do 1 minus that, because we want the probability that we do not draw a heart. We want the complement. You know, if event E is the probability of drawing a heart, we want the probability of not drawing a heart to complement. So we do 1 minus 13 over 52, which, as we saw earlier, works out to be, on a previous slide, we did this calculation for a different problem though, but it works out to be 39 out of 52. 39 out of 52. Okay. Now I want to move on to what's called expected value. Expected value is the average gain or loss of a procedure if it's repeated many times. There's missing a word there. Let me just add that word in. There we go. Okay. So basically that's what it is. It's the average gain. It's basically how much you should expect to win or lose in the long run. In other words, if you keep on repeating the procedure, whatever it is, you keep on repeating it many, many, many times, it's how much you should expect to lose or win. And here what we're going to do is focus on procedures where the outcomes involve money that you can gain or lose. Like prize money, for instance, or another place where this comes up is with insurance companies. You know, you buy a policy and if something happens, they insure you, that kind of thing. There is actually a way to calculate expected value. That's what I wrote down here. We'll go through some examples to illustrate it. Essentially, what's going to happen is you look at each possible outcome from the procedure. You consider how much money you win or lose from that outcome. You multiply by the probability of that outcome, and then you add up all the products. We'll see some examples shortly to illustrate that. So before we do that though, let me just say this. If you calculate the expected value and it's negative, then theoretically you don't want to play that game, because in the long run you're going to lose money. I mean, sometimes you might win. That can happen. Other times you might lose. In the long run, over time, you're going to lose money. If it's positive, however, the expected value, then theoretically you want to play that game repeatedly. I mean, sometimes you'll win, sometimes you're going to lose, but in the long run, you're going to win money. And sometimes the expected value could be 0. In that case, the game is considered fair. Okay, so that's the idea of expected value, but let's do some examples because I know it's not an easy concept. So for instance, let's suppose we're at a contest, okay, where each raffle ticket costs $3 to buy. There's one winning ticket and 150 tickets have been sold. The winner gets $300. What is the expected value to you of the raffle ticket? Okay, so what is the expected value here? Of course, we're assuming the raffle tickets are all equally likely to be chosen. Okay, so let's analyze this. So the two outcomes, of course, are your ticket, the one you bought, gets called and you win the $300. The other outcome is that your ticket is not the winning ticket and you don't win the $300. Okay? Well, if your ticket gets called, that is, if your ticket is the winning ticket, you win $300. However, remember, you paid $3. Let me put that dollar sign on the other side. However, you paid $3 for the ticket, right? So because of that, you're only really going to win $297. Okay? Again, this is the expected value to you. We're looking at this from your point of view. So you would win $297 in that case. Well, what's the probability of that? Well, there's only one winning ticket. So the probability of winning would be 1 in 150. 1 in 150. Okay, so what's that product? We get 1.98. That's what this product would be. 1.98. Okay, but what's the other outcome? You don't win. Your ticket is not the winning ticket. Well, in that case, you paid $3 for the ticket, so you're not getting the $3 back. So you would lose $3. That's what the negative sign tells us. What's the probability of that occurring? Well, if you don't win, you lose, right? So it would be 1 minus 1 over 100, 1 in 150, which is 149 in 150. I mean, I guess you really didn't have to do this subtraction, because if there's one winning ticket, there's 149 losing tickets. What's the probability of having a losing ticket then? 149 in 150. Okay, so what's the product here? We get negative 2.98. So now we add up these products and we get negative $1, or negative $1, I should say. So what is this telling us? In the long run, if we were to play this contest, so to say, or enter this contest, so to say, many times, if we repeated the contest, if they repeated the contest, excuse me, many times, we would expect to lose $1 in the long run. So theoretically, it's not a game you should play. I mean, sometimes you might win the $300. That can happen. But in the long run, you're going to lose $1. Okay. Well, let's modify this a bit. Let's say now the winning prize is higher. It's $453 now. What is the expected value now? That is, what is the expected value for us now? Well, it's the same idea, right? The only difference really is that if you have the winning ticket, you're going to win more money. You're going to win $450, okay? You're going to win $453, but again, you lose $3 because you paid for the ticket. So the only difference now is you're going to win $450. I put the dollar sign on the other side again. Okay. It was on the wrong side before, so I just fixed that. Okay, so we have now $450. The probabilities are still the same. There's only one ticket, and they still sold 150 tickets altogether. So the first product here is going to change. We have 450 times 1 over 150. Well, that turns out to be 3. The other outcome and product are the same, excuse me. So now the expected value for us, it's 3 plus negative 2.98, or 3 minus 2.98, same thing, which is 2 cents, 0.02. So theoretically, we should play the contest and enter the contest, that is. I mean, 2 cents is not a lot, but in the long run, we're going to win money, is what this is saying. Okay, well, let's do another example. An insurance company now estimates the probability of an earthquake in the next year to be 0.0013. Probability you could express as decimals. That's fine. You just convert fractions to decimals. And let's say the average damage done by an earthquake estimates to be $60,000. So what does this mean? Well, if you buy a policy from the company and an earthquake occurs, they're going to have to pay $60,000 for the damage done. If the company offers earthquake insurance for $100, what is their expected value of the policy for the company? Keep in mind now we're looking at it from the company's point of view when they gain money or lose money. Notice also if someone buys a policy, they pay $100, that's profit to them. They gain $100. Okay, so what's going to happen? Well, the two outcomes are there's either an earthquake or the earthquake does not happen.